Okay, yeah. Hi, everyone. I'm Drew Jamieson. I'm a postdoc at the Max Planck Institute for Astrophysics. And this talk, I'm going to be presenting some work from a recent paper with Angelo Caravano and Ichiro Komatsu, where we're kind of thinking a little differently about the initial conditions of the universe where you have primordial non-Gaussianity coming from inflation. And the idea is to simulate the nonlinear dynamics of inflation in order to generate realizations of the primordial curvature potential. And so why would we simulate inflation? Well, there's a few reasons. One is if you want to study primordial non-Gaussianity beyond, say, standard bispectrum templates, if you have some form of the bispectrum that we can't efficiently generate realizations of, maybe the best way to do it is just to simulate the physics that generates that bispectrum. Or if you want a sort of physically realistic and non-trivial hierarchy of endpoint correlation functions, we don't really have a standard method for generating a field that has those statistics embedded in it. But we can simulate the physics that would do that. A lot of the simulations of inflation started with studying non-perturbative regimes of inflation where you have, say, strong back reaction. In that case, you basically have to simulate the nonlinear dynamics in order to make predictions of what's going to happen. And so, of course, this, the outcome of simulating inflation is that you generate a field that you can then use for, say, maps of the CMB or running simulations of large-scale structure. And so I wrote a new code to do this because the codes that kind of existed, like ESI lattice or Cosmo lattice, they're codes that solve the equations of motion in real space using finite difference schemes for spatial derivatives, which is not really precise enough because you get the wrong dispersion relation, you get the wrong phase evolution, and then you're going to get the bispectrum and trispectrum wrong. So I wrote my code to be a pseudospectral code, so I solved the equations of motion in Fourier space, and then I implemented a ton of different innovations that make it very precise. So I use Fourier transforms to evaluate nonlinear terms, the mode convolutions. I smooth the fields before I do this because in inflation, you have vacuum fluctuations that have a huge amount of power, but those should just be oscillating linearly. They shouldn't be affecting the larger scales nonlinearly, and so you kind of have to regulate those. We solve our equations of motion using a high-order Runge-Kutta scheme that's also an embedded one. So we do error tracking through our numerical integration, which lets us do set thresholds and do dynamical time stepping through step projection and then repeating with a smaller time step. And then finally, oh, there's a video that's supposed to be playing. Finally, I implemented this temporal grid refinement because the only modes you're really interested in are ones that are kind of near horizon crossing at any given scale. Larger scales than that, they've frozen out, and smaller scales than that, as I said, they're really just vacuum fluctuations that should just be linearly oscillating. So throughout the simulation, I will inject more and more and more small-scale modes by increasing my grid size over time. And that way, I don't waste a lot of time simulating the very quickly oscillating small-scale modes that aren't really doing anything until much later in the simulation. And then by the end of the simulation, we have some realization of the primordial curvature potential. So the model that we simulated is this axion-U1 inflation model. So in this model, the inflaton is an axion-like field, and it has a Chern-Simons coupling to some U-engaged field, so like a photon field. So what does this model do? The phenomenology, just really briefly, is we have some wave operator on our gauge field, and normally this would be 0, but in the presence of this axion-like field, it is sourced linearly at leading order by a term that's coupled to the inflaton background time derivative and the curl of the gauge field. So that's just the magnetic field. Now, the curl is positive for right-handed modes and negative for left-handed modes, and so it distinguishes, but the sign is different for right and left-handed modes. And that means you generate chiral photons. So depending on the sign of the coupling constant and the inflaton's time derivative, you exponentially enhance one of the helicities. So say you exponentially produce lots of right-handed photons, but not left-handed ones. That's step one. If that were all that would happen, then those photons would just redshift away and nothing would happen. But in the inflaton's equation of motion, you have a kind of standard Klein-Gordon equation, an expanding universe, but it's sourced non-linearly by E dot B. So electric field dot magnetic field. This is, first of all, a parity odd term, because the electric field is parity odd and the magnetic field is parity even. And this is nonlinear, so it's giving you basically parity violating primordial non-Gaussianity. And then that imprints onto the inflaton, which then imprints onto the primordial scalar curvature potential. So you end up with corrections to your 2-point statistics. You end up with a 3-point statistics that's roughly equilateral peaked, but differs very much from the equilateral bispectrum template. And then you can also get 4-point statistics that are parity even and parity odd, which I kind of flash here briefly, but I'll show some of these things in more detail in a little bit. So again, we have this video of the simulation, and I'm showing various statistics of the simulation. So here, kind of in the middle at the top, we just have the vacuum power spectrum. And then over on the right, we have the sourced power spectrum, so the one that's coming from this E dot B term, and correcting, giving contributions to the power spectrum. And then at the bottom, we have the bispectrums. We have this temporal grid refinement. And so as we go, we inject more modes, so we get more bins of things later on. That early would just be fluctuating and not doing anything, but everything kind of comes in. And then you see at the end of the simulation, all the modes start to freeze out, and you get the primordial power spectrum, the source power spectrum, and the bispectrum. So this is kind of how these simulations work. And so for the power spectrum, we have a standard vacuum power spectrum. We just chose a potential for the inflaton that gives us this, standard kind of, AS is like 2 times 10 to the minus 9, NS is like 0.956 or something. And so those are the red dots at the top. And then as I vary the coupling constant, I have a sourced power spectrum that increases if I increase the coupling constant. And you can see it's like strongly blue tilted. The source power spectrum increases for small scales. It also has some running in it. And so this is like corrections to the power spectrum, right? We can put constraints on the model based on whether or not we see an elevation of small scale power. I would say also there's kind of standard analytic calculations that are done for these models, and these results actually differ kind of pretty significantly from those. So simulating them gets you more accurate results in this case. And then we have the bispectrum, where first at the top, we can see the shape of the bispectrum, which the blue is the highest amplitude thing, which is over on the top right corners of these panels, which is the equilateral shape. So it's peaked in the equilateral. But again, if we look at just the equilateral configurations of the bispectrum, it's strongly blue tilted. It's got this increasing slope. It also has some running in it. So it's pretty different from the standard shape. Also, just like the overall shape of the thing, it's kind of peaks in the equilateral, but the whole shape is not well described by a sum of local equilateral and orthogonal, even if you include this kind of tilted thing. The whole thing is really a non-separable form, which is the non-trivial thing here, right? We've generated a field that has this bispectrum in it that you can't really generate using the standard methods. And then we can use this bispectrum, right, giving constraints on FNL equilateral, right? It's not really the equilateral template, but if you went looking for equilateral bispectrum, you'd put some constraints on this model. So based on, say, the Planck bounds on FNL equilateral, depending on what L max you go to, you constrain the coupling constant between the axion and the gauge field. And so, of course, this is a bit of a crude analysis. You could do something more careful, which we hope to do, but already you can see there's some regions of parameter space for the coupling constant that are just going to be ruled out because we don't see an equilateral bispectrum. And because it's blue tilted, as we go to smaller scales, we get very strong improvements in the constraints. We can look at higher order statistics, right? So I showed kind of the trispectrum, just flashed it earlier because we have not finished analyzing this. But we can also look at things like 1-point statistics, so I can take my primordial curvature potential and perturbation, and then convert it to the linear matter field, right? Applying the transfer functions, and then look at what the 1-point statistics are like, and then I can look at what, say, reduced cumulants are like, so the 3rd and 4th and 5th reduced cumulants, and you can actually distinguish this from like a single field theory of inflation, which is almost perfectly Gaussian, very little non-Gaussianity. And here we see significant, 3rd order cumulant, 4th order cumulant, and you can still detect the 5th order one. So there really is some kind of non-trivial hierarchy of endpoint correlation functions embedded into this field that would be, very difficult to generate using some other way that would actually reflect the physics of this model. So then just I'll end with the most exciting thing, which is like how well converged are these simulations. This is the hardest part, actually, which is as you increase the resolution, again, like I said, you have these like vacuum fluctuations that are quite large, because vacuum fluctuations are in, say, quantum field theory. So as you increase the resolution, if you do this naively, you'll kind of blow everything up on larger scales eventually. But with the smoothing scales that we've chosen, and we do things very, very carefully, we see very converged results as we increase the resolution for both the power spectrum and, say, like the equilateral configurations in the bispectrum. We also have kind of chosen the smoothing scale for these nonlinear things to vary it, so that basically it's in a region that's kind of flat here. So this is like the smoothing scale, and if you change it too much, your results will be very sensitive to it. So we pick it to be in a region where things are not so sensitive. That's do it. And also, of course, you need to choose both the time that you start the simulation and how early you inject modes. Because if you inject them too late, you're going to miss some of the nonlinearity, and your results won't converge with respect to start time. And so this is like how many e-folds before horizon exit do the modes get injected, or does the simulation start? And if you start at, say, 2 or 2.5, it's not really early enough. But any time after that, 3 e-folds to 5, it works really well. So the results are really nicely converged. And so we have this new code. It's a very high precision code for simulating the nonlinear dynamics of inflation, and it predicts this like rich phenomenology, this blue tilted correction of the power spectrum, bispectrum, higher order correlation functions, including a parity odd part of the trispectrum. And going forward, we'll be doing this analysis of the trispectrum more carefully. We could easily add metric perturbations to get the chiral gravitational waves that you would generate during this model if you put the energy scale high enough. And of course, we can then use this to run n-body simulations to study large-scale structure from axion-U1 inflation. Okay. Thank you.